Okay, so today we're going to be looking at the concept of limits. If limits were part of the calculus main course meal... Hang on, let me start just one more time. I've got an analogy, I just need to get it word for word perfect. Welcome to this episode. We're going to be looking at limits. If calculus were this big feast, limits would be the appetizer. So, we're going to be looking at some algebra today, and this is sort of the fundamental link between limits. So we looked in the last video at first principles, and we looked at the limit as h approaches 0. What's really happening here is we're having 2 points, getting closer and closer together, and they can't exactly be on top of each other, but they're getting very, very close. This is a really zoomed in image. But now, let's just get our head around this a little more. It's not just the limit as h approaches 0 that's a bit of a problem in algebra, but we want to actually know what a function is approaching before it's undefined. So what does that mean? Well, say I have the function f of x equals 3x x plus 2, and I wanted to actually find the f of negative 2. Well, guess what? Unfortunately, I cannot. The reason being, if we have negative 2 as x, then what we're going to end up with is negative 2 plus 2, which is going to ultimately equal an undefined result. Because when we divide by 0, we cannot actually get a value or a result from it. It's undefined. Imagine if I had this pencil and I tried to divide it into 0 parts. You just can't do it. It doesn't really make sense. But this is just a small hole on an otherwise perfect function. A small part where it's temporarily undefined if the function we were travelling along reaches there. How do we come across this? Because we want to know roughly where this little undefined hole is. And that's where we use limits. So, just to break this up into another little analogy here, imagine that we're driving along and we're going on a vacation to the Grand Canyon. We're using a little GPS unit to get there. Now what we want to actually do is we want to make sure that we don't end up in the Grand Canyon, because of course we don't want to drive through the Grand Canyon. Wouldn't be a good idea. But we want to get quite close to the Grand Canyon so that we can actually take a picture of it and actually go to the tourist attraction park they have there. Well, in order to do this, we look at where we roughly are before we actually get into the Grand Canyon. And, of course, you would obviously see what's actually happening in terms of your location when you get close to it. And that's where the limit comes in handy, because we're getting close to it, but not actually being at it. Okay. So I'm going to show you an example of solving a limit. So, an example I have here is that we want to find the limit as x approaches 3 for the function x squared plus 5x plus 6 on x divided by 3. Right off, we know x take 3, sorry. Right off we know we have a problem. Because if we substitute in 3 for x, we're going to end up with 3 take 3. The good thing is, there's a simple solution to actually find out what's happening to the function before we hit 3. In order to do this, we need to factorise the top bar algebraically. And we all know how to factorise some linear algebra. If not, we could always use the quadratic equation. purpose of this video, I'm going to assume that you know how to factorise an expression like this. If you want to, feel free to have a go at the quadratic equation. In this case, we would have a equal to 1, because that's a coefficient of x squared. We'd have b equal to 5, because that's a coefficient when we have the term 5x. And we would have c equal to 6. If you were to factorise it, you should actually find that it comes to this. And if you're not sure, you can always expand it again, just to double check. X squared, take 2x, take 3x, don't you hate it when that happens? Shit. I thought it looked wrong. I'll go through it again, don't worry. So let's take it from the top. That was so bad. I thought it looked wrong. I was like, wait, there should be at least one negative in there. That's what I was thinking to myself. Okay. So let's actually have a look at an example here. Let's find the limit as x approaches 3. For x squared, take 5x plus 6 over x, take 3. Right off, we know there is a problem, because if we substitute x as 3, we're going to have a denominator of 0. And when we have a denominator of 0, the entire function is undefined. So what we do is we factorise the numerator. For the purpose of this video, I'm going to assume you know how to factorise an expression like that. If you don't know, you can always use the quadratic equation. X equals negative b plus or minus the square root of b squared take 4ac on 2a. In this case, a would be equal to 1, because that's a coefficient of x squared. B would be equal to negative 5, because that's a coefficient of this term here. And then c would be equal to 6. So now, when we factorise it, we should get x take 3, x take 2. If you're not sure, you can always check. X squared, take 2x, take 3x, plus 6. Because remember, negative 3 times negative 2 is going to make positive 6. And hence, voila, we get x squared take 5x plus 6. That means we've factorised correctly. All over x take 3. Now hang on, we can do some cancelling here. How can we cancel? Well, we have these two terms multiplied by each other. So that means we can say goodbye to x minus 3. And we're left with an expression that we can calculate. So hence, what we use is we have our x take 2 remaining, and we simply substitute the x for 3. Therefore, the limit as x approaches 3 is going to be 3 take 2, which is equal to 1. And this gives us an idea of what's happening when the function is actually approaching an x of 3, even though it is temporarily undefined. Thank you very much for watching. Hopefully this was helpful. Again, this gives you a rough idea of the y-coordinate of what's happening. So, again, I'll see you next time, where we're actually going to look at some differentiation rules. That's all for now.